Good morning, everyone. This is Sachin Piske from Electrical Engineering Department, S&D College of Engineering and Research Center. In the previous lecture, we discussed about asymptotic approximations. Now, we are moving towards phase margin and gain margin. So, let us discuss some points which are very important for us in control system engineering. In university examination, generally the question arises based on gain margin is define gain margin and explain how it is found using Bode's law. So let us start. Gain margin, a measure of relative stability, and it is defined as the magnitude of the reciprocal of open loop transfer function evaluated at the phase crossover frequency, that is omega PE, and which is frequency at which the phase is minus 180 degree. That is, gain margin is equals to 1 upon GH of J omega PE, where angle GH of J omega PE is equals to 180 degree. Let's see here. One feedback control system is given. First block is K and second block is plant or control system. So it is indicated as K and G of S. Let's say that we have the following system as K is a constant, that is variable constant gain, and G of S is the plant under consideration. The phase margin is the change in the open loop phase shift required to make a closed loop system unstable. So the gain margin is actually defined as the change in the open loop gain required to make the system unstable. System with the greater gain margin can withstand greater changes in the system parameter before becoming unstable in a closed loop. Keep in mind that unity gain is a magnitude which is equal to the gain of 0 in dB. The phase margin is the difference in phase between the phase curve and minus 180 degree at the point corresponding to the frequency that gives us a gain of 0 dB. The gain crossover frequency omega GC. Likewise, the gain margin is the difference between the magnetic curve and 0 dB at the point corresponding to the frequency that gives us the phase of minus 180 degree. This phase crossover frequency is denoted as omega BC. Now, graphically, this gain margin can be computed by drawing a vertical line upward from the phase crossover frequency as shown in this figure. It is possible to examine the part of the Bode plot to determine the gain margin by which the system magnitude can be changed to make the system marginally stable. The gain margin in dB is the distance on the Bode magnitude plot from the magnitude at the phase crossover frequency up to the 0 dB point. Let's see this diagram. This omega GC is shown here. Means as per the Bode plot, we are going to consider the x-axis and y-axis. So y-axis is a constant line and x-axis is taken, that is 10 to the power 0, then 10 to the power 1, 10 to the power 10, then 10 to the power 100. Likewise, we are taking the point. So here, this red arrow indicates WPC, and this means the gain margin, and 1 WBC is shown. The gain margin in dB is basically The distance on the Borel magnitude plot from the magnitude as the phase crossover frequency up to 0 dB point. Now, this we are moving towards the phase margin. Phase margin, that is phi pm, is a measure of relative stability and is defined as 180 degree plus the phase angle phi 1 of the open loop transfer function at unity gain, and that is phi pm is equals to 180 plus arg gh of j omega gc degree, where gh of j omega is equals to 1 and omega gc is the gain crossover frequency. It is also shown in figure. Phase margin is computed by drawing a vertical line downward from this gain crossover frequency, that is omega gc is the frequency at which the magnitude is 0, that is 20 log of 1 is equals to 0 dB. This is shown in figure. This command basically returns the gain and phase margin and this gain and phase crossover frequency and a graphical representation of these on particular border plot. So this gain margin is equals to 13.26 dB, that is omega is equals to 5.477, and this value of phase margin, that is pm, is equals to 100.7, means omega is equal to 1.848. So here the margin can be considered 50 and in another 1930 to 40. See here is margin magnitude dB is equals to g into omega, and that can be considered as a constant value 20 log of j omega. So what is the phase shift? Phase shift, that is g of j omega or simply omega, can be considered as 180 upon pi argument g of j omega minus 360 if argument g of j omega is greater than or equal to 0 and 1. Let us assume this value of k is equals to 2. Therefore, g of s is equal to k upon s into 1 plus s or s plus 1 in another bracket 1 plus s by 3. Now, some definitions or bandwidth are there. So we are moving towards this definition by considering this process criteria. Basically, the Nyquist plot allows us also to predict the stability and performance of closed loop system by observing its open loop behavior. The Nyquist criteria can be used for design purpose regardless of open loop stability. That is, Bode design method is assumed that the system is stable in open loop, and therefore we use this criteria to determine the closed loop stability when the Bode plot display confusing information. This Nyquist diagram is basically a plot of g of j omega, where this g of s is the open loop transfer function and omega is a vector of the frequency which encloses the entire right half plane. While drawing the Nyquist diagram, both positive and negative frequencies from 0 to infinity are taken into account. In the illustration, we represent the positive frequencies in red and negative frequencies in green. This frequency vector used in pivoting the Nyquist diagram usually look like this. However, if we have open loop pole or zeros on j omega axis, g of s will not be defined at those points and we must loop around them when we are plotting the contour. Such a contour would look as this. Now, the Cauchy's criteria. The Cauchy's criteria states that when taking a closed contour in a complex plane, and mapping it through a complex function that is g of s. The number of times that the plot of g of s encircles the origin is equals to the number of zeros of g of s enclosed by the frequency counter minus the number of poles of g of s enclosed by the frequency counter. This encirclement of the origin are counted as a positive if they are in the same direction as the original close counter, or negative if they are in the opposite direction. Where studying feedback control, we are not as interested in job as in the closed loop transfer function. Let us consider one transfer function, that is g of s upon 1 plus g of s. If 1 plus g of s encircles the origin, then g of s will enclose the point minus 1. Since we are interested in the closed loop stability, we want to know if there are any closed loop pole, that is zeros of 1 plus g of s in the right half of the plane. And therefore, the behavior of this Nyquist diagram around minus 1 point in the real axis is very important. And however, the axis on the standard Nyquist diagram might make it hard to see what is happening around this point. So what is gain margin? Since gain margin is defined as the change in the open loop gain expressed in decibel, requires at 180 degree of the phase shift to make the system unstable. Let's see this diagram. So first of all, let's say that we have a system that is stable if there are no Nyquist encirclement of minus 1, such as 50 upon s cube plus 9s square plus 30s plus 40. So these Nyquist stability criteria applications are there. Knowing this number of right of plane, same diagram can be considered before. If z is equal to p plus n is positive non-zero number, then the closed loop is unstable, and we also use the Nyquist diagram to find the range of the gain for a closed loop unity feedback system to be stable. So considering this example where g of s is given as s square plus 10s plus 24 upon s square minus 8s plus 50. Now, what is the bandwidth? Depending upon the Nyquist stability method, how this bandwidth can be defined. So this bandwidth of the system is that the range of the frequency of the input for which the system responds satisfactorily. Satisfactory performance is determined by the application and the characteristics of a particular system. Let us take an example. The audio amplifiers are often compared on the basis of their bandwidth. So, as an ideal high fidelity audio amplifier has a flat frequency response from 20 Hz to 20 kHz. That is, it has a pass band or bandwidth of 19,980 Hz. This flat frequency response means that the magnitude ratio of the output to input is essentially a constant for the bandwidth. Hence, signals in the audio spectrum are faithfully reproduced by a 20 kHz bandwidth amplifier. Often, the bandwidth of a system is defined as that range of the frequencies over which the magnitude ratio does not differ by more than -3 degrees from its value at a specified frequency. For many feedback control systems, bandwidth is in this case equal to cutoff frequency, that is omega s. What is this? What is cutoff frequency? That it is indicated by c for omega c. The frequency omega c at which the magnitude of closed loop response is 3 dB or below, and its zero frequency value is called as cut-off frequency. Some more definitions are there, that is cutoff rate. So the cutoff rate is the frequency rate at which the magnitude ratio decreases beyond the cutoff frequency, that is omega c, and it is nothing but the slope of log magnitude curve near cutoff frequency. For example, the cutoff rate may specified as -6 dB per octave. And as we already discussed what is octave, 20 to 200 kilohertz range generally it can be sustained. What is MP? MP means reasonable peak frequency. The resonance peak MP, that is resonance peak frequency, a measure of relative stability, and it is the maximum value of the magnitude of the closed loop frequency response. This resonance frequency omega p is the frequency at which MP occurs. Now, what is relative stability? The relative stability of a particular system is indicated by the gain margin and the phase margin in terms of the system open loop frequency response. Consequently, these parameters are easy to determine from model plot of GH of J omega. Since 0 dB corresponds to the magnitude of 1, the gain margin is the number in dB that GH of J omega is below 0 dB and the phase crossover frequency, that is omega PC. The phase margin is the number in degree of angle GH of J omega above -180 degree and the gain crossover frequency omega GC. In most of the cases, this positive gain and phase margin is defined above will ensure the stability of a particular closed loop system. Also, for the stable system, omega GC is less than omega PC, that is GM and PM are positive. And for unstable system, omega GC is greater than omega PC, that is GM and PM are negative. And it is shown in this diagram. See this diagram, one zero line will be given. So negative or unstable region will be shown from -12 to 0 line, and from 0 to 12 on the upper side it is considered as a positive system, that is a stable system. So according to this, G of omega is equal to 0.64 upon J of omega into J omega square plus J omega plus 1. Here we are going to consider this phase margin is equal to 30 degree. On the basis of this phase, we estimate sigma is equal to 0.30 as given degree is having the 30 value. So MPW is equal to 9 dB and MPW is equal to 2.8 and omega r is equal to 0.88. So from this equation, this MPW is equal to 1 upon 2 sigma to under root of 1 minus sigma square, and value of sigma is 0.80. So we are confronted with this conflicting, as the apparent conflict is caused by the nature of J omega, which slopes rapidly towards 180-degree line from the 0 dB axis. The designer must use the frequency domain T, time, and domain correction with this cause. In this, basically this log scale uses the principle that when the ratio between 2 points is same, the 2 points will be separated equally, and for example, it is considered as 10, 100, 1000, 10,000, etc. So, a commercially available semi paper is shown. Let us observe that the top left hand side contains the number written as 1, 2, 3 up to 9, and up to 9 we again have 1, and the same cycle which is repeated from 1 to 9. This is x-axis, and on y-axis is a normal scale that is equally spaced scale. Each bold line on the y-axis is 1 inch and is subdivided into 0.1 inch, each with 0.5 inch slightly darker. We plot the magnitude and phase on this scale. Since both the graphs must be drawn on the same paper, scale must be chosen properly. Suppose we choose the leftmost as 1 most one as 0.1 rad per second. Then the next one will be 0.1 into 10, that is equals to 1 rad per second. And similarly, the next one will be 10 rad per second, and so on. That is 10 times the previous value, and it is called as a decade apart. Hence, the first two for the above scale is 0.2 rad per second. Next two is the 2 rad, then 20 rad per second, and 200 rad per second, and so on. That is 2 into the value of 1 in that particular cycle. Make sure you have understood the above marking. Take any random frequency and see if you can identify and it on x-axis of your semi-log paper. Now we are moving towards the y-axis representation. So this is our ordinary scale, which we are familiar with. In graph 1, we plot the magnitude in dB and on in y-axis, and in graph 2, we plot the phase angle in the degree on y-axis using some suitable scales. This frequency of the transfer function can be written integralized from as a ratio of the polynomial. It must be factorized to obtain a general time. Okay. In this way, we can easily find out the phase margin and gain margin. Thank you.